Hello everyone. So in the previous lecture we talked about Euler circuits and Euler trails, and we saw the conditions that are required for a particular graph to be Eulerian. But we did not talk about how we can find an Euler trail or an Euler circuit. Okay, and you might say, well, if I have a graph, for example, like this, and as long as the conditions are there for having an Euler trail or an Euler circuit, then I'm just going to take my chance, start at any vertex, and through trial and error, I will try to find an Euler trail or an Euler circuit. However, suppose you have a highly connected graph with a lot of vertices and edges. There needs to be a systematic way in order to find an Euler trail or an Euler circuit. In other words, there has to be an algorithm that aids us in order to do so. And that is basically what Fleury's algorithm does. Fleury's algorithm is an algorithm that we can use in order to find Euler circuits and Euler trails. Okay, so through solving this example right here, I'm going to show you what Fleury's algorithm is. So suppose we have a graph like this, and I want to find an Euler circuit. First of all, let me see if the conditions are there. So is the graph connected? Yes, it is connected. Do I have all the vertices to have even degrees? Well, this vertex right here has degree 2, this one is 2, this one is 4, and then 2, 2. So all the vertices have even degrees. So I do have the conditions for having an Euler circuit. And definitely I do have an Euler trail, but I'm going to find an Euler circuit. So let's see how we can find an Euler circuit using Fleury's algorithm. Basically, what you do is you will create a replica of your graph, okay, somewhere. So let's create a replica. This is D, this is A, this is B, this is E, and this is C, and I have edges like this. Okay, so this is a replica of my graph. Then what I'm going to do is, since I do have the conditions, I can start at any vertex I want. So suppose I'm going to start at this vertex, and then I'm going to take this edge. Okay, whatever edge I take, I will delete it in my replica. If the deletion of that edge makes the graph to be disconnected, then I will not take that edge. And you'll see what I mean in a second. So since I took this edge right here, I'm going to delete this edge right here. And then what I'm going to do here, I have three choices. I can take this edge, or this edge. So here, suppose I take this edge, okay? If I take this edge, then I'm going to delete this edge right here. And as you can see, if I take this edge and delete it, then the graph that I have will be disconnected. Therefore, I'm not going to take this edge right here, okay? If I am at B, okay, and I have come from D, I'm not going to take this edge that takes me to A. If I do that, then I'm going to have a dead end, and I'm not going to have an Euler circuit. Because, so let me bring back this edge right here, because by deleting any of these edges, the graph will not be disconnected. So therefore, I'm going to take this edge right here, and I'm going to delete this edge. Okay, so this is the path that I've taken. I started at D, and now I am at E. And now I'm forced to go to C, and then I'm going to delete C. And then I'm forced to go to B, and I'm gonna delete this edge right here, and then everything from here is forced on me. Okay, and now I do have an Euler circuit. Okay, so basically what you do, you start at a vertex and you go through an edge that is attached to that vertex, and then you delete that edge in your replica. Okay, if deleting that edge in the replica makes the graph to be disconnected, then you do not go through that edge. You go through another option if you have. And then you repeat this process until you have an Euler circuit. Okay, so let me just show you what happens if I... So I have an edge right here, an edge right here, an edge right here, and an edge right here. So as you can see, I started at D, and then I went like this, okay, and then I kept going. But suppose I don't keep going. I go from B to A. So if I take this edge right here, I am forced to take this edge, okay, and I am back to D, and I cannot go through this edge right here again to go to B because that will be a duplicate, and I have not visited this edge, or this edge, and I don't have an Euler circuit. Okay, so that's why it's very, very important if you are using Fleury's algorithm in order to find an Euler trail or an Euler circuit. When you go through an edge and you delete it in your graph, okay, or in your replica of the graph, if that makes the graph to be disconnected, then do not go through that edge. Go through another one. Repeat this process and eventually you will get an Euler circuit or an Euler trail. Okay, for an Euler trail, you start at an odd vertex, okay, you use this mechanism, okay, and eventually you will end up at the other odd vertex. Okay, so let me give you another example. Suppose I have this graph right here and I want to find an Euler circuit again. So let's use Fleury's algorithm in order to find an Euler circuit. So this is my replica right here. This is vertex A, this is vertex B, this is vertex G, and then H, and then C, and then F, and then J, and then E, and then D. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. So these are connected like that. And then I have an edge right here. And then from G to H, I have an edge. And then I have an edge right here. And then an edge right here. And then an edge right here. Between H and E, I have an edge. Between C and J, I have an edge. Then I have an edge right here, like that, and like that. Okay, so this is the replica of this graph that I have right here. So suppose I'm going to start right here, and then I'm going to go like this, and then I'm going to delete this. As you can see, the graph is not disconnected yet. That means I'm on the right path. So I'm going to go like this, and then I'm going to delete this edge right here. And then I have a choice to go through this edge, or this edge. If I go through this edge and I delete this, the graph will be disconnected. So definitely I cannot go through this edge. So either I'll go through this or this. So I'm going to take this edge. And I'm going to delete this edge right here. Okay. And then I have a choice to go like this, or like this. So what I'm going to do is I'm going to go like this. And I'm going to delete this edge right here. The graph is not disconnected. Okay. Now I have a choice to go like that, okay, or like this. As you can see, if I go like this and I delete this edge, the graph will be disconnected. So no, I cannot go through that edge. I'm going to go through this option right here, and then delete this. And then I'm forced to go like this, and I'm going to delete these two. And when you have vertices like that with no edges being attached to them, just delete them. You don't need them anymore. Okay, and now I have a choice to go like this, or like this. So as you can see, if I go from E to H and I delete this edge, the graph will be disconnected. So definitely no, you cannot go through that edge. And try it. Suppose, so let's do it in blue. Suppose I go like that, okay? And then I cannot go through this edge or this edge. I'm forced to go like this and then like that. As you can see, I have left 1, 2, 3, 4 edges. That's why Fleury's algorithm actually works. Okay, when you reach an edge, okay, and by going through that edge and deleting it makes the graph or the replica that you have right here to be disconnected, no, do not go through it. That will not give you an Euler circuit. So now either I will go like this or like this. So I'm gonna go like this, and then here, by going like this, and then here the graph will not be disconnected. And then I'm gonna come like this, and then like this. As you can see, by going like that, the graph will not be disconnected. And then eventually I'm gonna go to my starting point, which is A. So I started right here and then I finished right here. And if I deleted these edges and vertices, right here I have an Euler circuit. Okay? So that is basically how Fleury's algorithm works. By deleting the edges in your replica that you go through, if you make the graph that you have to be disconnected, then that's a sign that you should not go through that edge. If not, then go through it. By repeating this process and starting at a vertex, you will eventually end at the vertex and you have visited every edge exactly once in your graph. if you are looking for an Euler circuit. If you are looking for an Euler path, start at an odd vertex, do this process, okay, go through an edge. If the deletion of that edge makes the graph to be disconnected, don't go through it. If it doesn't, go through it. Eventually, if you repeat this process, you will end at the other odd vertex. Okay, so that is about Fleury's algorithm.